School. I'm Anil, and this is the first lecture on supervised learning. We will look at the simplest and the most primitive of the machine learning paradigms, the supervised learning models. And in subsequent lectures, you will look at more complex models like deep networks, graphical models, and so on. In this part of the lecture, we will begin with some very basic examples that help understand the kind of use cases where ML models are a good fit. And then we will see what kind of ML models we can train with supervision, and the constituent or the basic parts like the loss function, the modeling function, and so on, that we will need to train the model. Some basic theory, basic but very important theory that will recur in subsequent lectures as well. It's very important to understand this because generalization is at the heart of all machine learning models. And then we'll look at the simplest of supervised learning models, the linear models, simplest but some of the most used models, and how we can train these models by using optimization algorithms. Let's look at a very simple example of address deliverability. Let's say we are given an address and we want to identify if the given address text is good enough to deliver to that place. And as you can see in the records on the slide, if you're just given a broad locality, it's very hard to deliver to that place. And the ML model assigns it a very low score, the address deliverability score, ADS, which you see in the second column. As you improve the address by adding more details, like the building name, the road, the street where this building is, the floor, the building that it has to be delivered to, a landmark, the score keeps improving. And this helped reduce the number of address not found problems at the time of delivery by almost 50%, significantly saving logistic costs. A similar application on product packaging. We do not want to use packaging that is too big and wasteful for a product. On the other hand, we don't want to use inappropriate packaging and cause damage leading to losses. So we want to use the right packaging that balances both products safe delivery and reduces the cost. We should in fact take into account, apart from cost, aspects like, is it fragile? Is it an electronics good? Is it food? The kind of the various features of the product before deciding on whether a packaging is appropriate. And rather than making decisions manually, moving to an automated system has significantly reduced damage costs and saved operational expenditure. Farm produce grading is a similar problem, and is a very well-known problem. We want to quickly grade vegetables and fruits so that we identify the bad ones and remove them to ensure only the good ones are delivered to the customers. And moving from manual to automated has significantly reduced grading costs. Design insights. The Amazon product pages typically contain a lot of information, and it is sometimes the information that the customers are looking for. Uh, they'll have to browse the detailed pages and maybe even read the reviews if they want to understand what customers who have used these products think of them. And mining and extracting these attributes and other qualities of the products from unstructured raw text and making it readily available and available in the form of a question answer format is very important for customer experience. And this is again a good fit for machine learning models and systems. Broadly speaking, what are the models that what are the use cases where we would want to deploy a machine learning model? So if something is deterministic, we could simply write the logic, code the logic down. But when we have a problem that is not deterministic, like handwriting recognition, we would rather have a model that takes into account the randomness. Not everybody writes the number 2 in the same way, and yet we can recognize it, and we would want machines to do exactly the same thing. And this randomness, not completely arbitrary, but certain amount of randomness that can be learned from data, is a very good use case for machine learning systems. Similarly, those that we want to scale, if we have large amounts of data arriving at high velocity, like let's say there are lots of transactions, and we want to identify and detect any fraud transactions from among them. Similarly, when there are a lot of search queries arriving and we want to ensure we present the right set of results that relate to the intent of the user. These are good applications that fit into the machine learning paradigm. And finally, those where we want the algorithms to personalize depending on users' past history of purchase or past history of viewing content. We want to personalize and recommend those that they're going to like. These are some very good applications where machine learning systems have broad but important structuring of the ML pipeline. There are two parts to it, the training and the prediction part. The training involves historical data, which is nothing but observations from the past. And this historical data is what a learning algorithm uses to give out a model. And the model is a mapping from the inputs to the outputs that we want to predict. Here, the inputs are referred to by the variable x, xi, the subscript I being the index of the input. So let's say we have 100,000 samples or observations in the historical data. I would range from 1 to 100,000. Each of those inputs would have a corresponding target variable or an output, which we want to predict at test time. So the learning algorithm takes historical data, past observations, and it returns a model F that we could use for prediction at test time. And this prediction or inference is the second step, where we receive actual unseen samples where we make our predictions using the model F. So F is simply a mapping from X to Y. And this is what a learning algorithm gives us. Take a simple example of trying to predict what category a particular e-commerce page belongs to. Let's say we only have two categories, electronics and kitchenware. The input X would be a feature vector. It is certain features extracted from the web page. Things like, does it include uh, vocabulary that describes electronics, or does it include vocabulary that describes kitchenware? And do you see words like um, uh, battery and uh, uh, how many gigabytes is this, or what processor is that, things like this? Or do you see words like, is it Teflon, or is it non-stick, is it stainless steel, or things like that? So the vocabulary is indicative, representative of what category this could belong to. And that is exactly what is encoded in the feature vector in a numerical format. So imagine using binary features like, does it have the word stainless steel? Does it have the word Teflon? Does it have the word 16 GB? Does it have the word 64 GB? Things like this. I mean, it's too primitive to use features like this. And you'll see in later lectures that when you move to uh, deep networks and things like that, you no longer handcraft these features, but you rather learn them from the raw data itself. But even then, irrespective of what method or algorithm you use, you will always need to encode it into a numerical vector that contains that information. And this is what X here represents. It's the features or the attributes. It could be raw data like pixels of an image. Nevertheless, it's a numerical representation of your input. And Y in this particular example would be a binary class label that says whether it belongs to class electronics class label +1, or it belongs to kitchenware -1. You could have other kinds of Y, like numerical Y. If you are predicting the temperature or predicting uh, values on the stock market, you would have numerical values. And uh, you know, or if you're predicting from among a lot of classes, it would be a multi-class problem and not just two classes. The classes could range from 1 to, let's say, 100, if there are 100 different product categories and you're classifying into them. So depending on whether it is uh, classification problem where you have Y is discrete classes, or a regression problem if Y is a numerical number. So this broadly, the split into training and prediction is something very important uh, for us to note, especially because it is performance on the, the test sample at prediction time that is most important to us. And this performance on the test sample is what is called generalization. And we will come back to this in a few slides. But we do not have access to this test sample at prediction time. We will, however, have to train on the training sample or the historical data, but tweak the learning and tweak the learning process so that we get the best possible performance and expectation on the test sample. And we will revisit this in a few slides. But I just want you to note here that the distinction between training sample and test sample is very important. and it's really performance on the test sample that's what really matters to us. Takeaway is that you identify the problem and ensure you collect the right data. Uh, Data collection has to be done very carefully to um, make sure you have a faithful representation of the distribution that you're going to see at test time. It's test time sample distribution that matters to us. As a simple example, let's say you want to evaluate the efficiency of a drug or some medical testing procedure. Uh, let's say the procedure is intended for the medical test is intended for everyone above the age of 20. But when you want to test uh, this experiment with this and estimate its efficiency in your experiments, let's say you go offer university students some vouchers in return of volunteering for the test. Uh, your training data is just going to contain a sample of students from universities who belong to a certain age group or an age band. And this is not representative of the real world sample it's going to see when you deploy that in, let's say, a hospital. This is a clear case of your training sample being very different from what you're going to see at test. And you should ensure that such things don't happen when you collect your data. And then you extract your features. Once you extract your features, you then go through the process of training the model F, which you then deploy in production or use it at test time. We will now look at some the constituents of the supervised learning problem and how we can learn a model given such historical data. This is essentially the two broad kinds of supervision. If you have Y that's categorical, or it's just classes 1, 2, 3, 4, and so on, it's called a classification problem. And if your Y is numeric, you have a regression problem. Classification problem is like if you want to classify into one of the 100 products, or if you want to classify into the various categories you've got. And regression examples are like product demand forecasting or base price prediction and so on. This is a very broad overview of the various models from within the supervised learning approach. The simplest are the linear models, which we will look at in the later part of this section. Subsequently, others will cover tree-based models, neural networks, and other models like Bayesian and heuristics and so on. So what are the parts of this supervised learning model? The most important thing that determines the relation between the inputs X and Y is the mapping. Let's call that a function F, and F of X is a prediction of the prediction that you're making of that particular input, of which the true value is Y. So f of x is an estimate that you are making of y. The true value, for example, could be in a regression, let's say it's 33. F could be a very good model and it's making a very close prediction of 33.2, or it could be a very bad model and it's making a very far off prediction like 47. So f of x is an estimate of the true value y. Now, how do you determine if a particular f is a good model f or is it a bad model f? Because we eventually want a very good mapping that will tell us uh, whether it is usable, it's useful for us to make predictions or not. So we use what is called a loss function, which will tell us how good or bad a particular f is. So a very simple loss function for regression could be just the difference between the true value and the prediction. And that is what is called the squared loss. However, if you have a classification problem, the squared loss wouldn't work as well. So we have other losses. A simple classification loss is just a counting loss. Let's say you have 100 data points in your data set or training data D. And every time the model F makes a mistake on a sample, the loss simply adds a value 1. And if the model F gets it right, it does not add any penalty. It simply adds 0. That's a simple counting loss. It's a 0-1 misclassification loss. However, this particular misclassification loss, which is in fact a very good loss in terms of a lot of uh, properties, and that is what we would want to ideally optimize. It is not numerically amenable it is not amenable for optimization in uh, to solvers. That is because it does not have certain properties that make certain functions easy to optimize. So we have approximations like the logistic loss or the hinge loss, and these give us different models. But the key point here is that you have the function f, which is a mapping from x to y, and you correspondingly also have a loss that will tell you how good or bad the function is on a given data set D. And what we are doing here is computing this loss on each of the samples and summing it up on the training data D. And then we want that loss f, which minimizes this objective function uh, uh, that function f, which minimizes this objective, and we can call it the f star, and this is what we would use in prediction at inference time. Let's take a very simple example of a linear model. It's called a linear model because we're assuming that the function f is linear in terms of the feature variables x. So it's simply w transpose x or w times x, and it'll look just like any other linear equation. You have, let's say you have two variables, age and income. You have the first coefficient times the first variable, here 5 times age, and then the second coefficient times the second variable, here -3 -4 times the income. And then depending on whether you have regression or classification problem, you would use this f of x correspondingly. In regression, you would simply use the score coming out of this equation, but in classification, you will have to apply a classification rule on top of that score. Like for example, thresholding. You can do something like if the score is above 0, I'm going to call it class 1. Otherwise, it's class -1. Okay. So the point here is that in linear models, your f of x is linear. That's the key. So what exactly does the loss compute? Now that we have assumed that it's going to be a linear model, you can look at an illustration of the same example. We have two variables like age and income in the previous slide that we have seen. And it's going to be a two-dimensional space. And let's say you have a classification problem of blue and red points that you want to separate with a decision boundary. What does the loss really do? So the loss computes something like this. What you see on the right side is an illustration of various loss functions. This gray step that you see, the step function, is the 0, 1 misclassification loss that we talked about. The x-axis is the true value times the score. The score here, f, is just since it's a classification problem, it's the sign of W transpose X. Okay, it's the sign of the score or the sign of the model prediction f of X, and Y is the true value. Now, let's say this solid red line is the decision boundary. Take the example of this red point. This lies below the red line, and it is correctly categorized. Below the red line are all the red points. Below the decision boundary are all the red points. Y, for example, let's say for all these points that lie here, Y is -1. The corresponding f of x is also -1 here. When you take the sign of f of x, and when you take the product of these two, you get a positive number, and that is that's going to lie on the right side. So it's a good prediction. The model has predicted this correctly. And the same is true about this blue point, the plus above the red line. If below the red line, below the decision boundary, the prediction is negative, above it, it's going to be positive. And since we have assumed that the negatives have a true value, true class label of -1, the positives have a true class label of +1. So the prediction is positive, the true label is positive, the product is positive, it lies to the right side of 0. And all those points, both these points are correctly classified. And as per this loss function, they're paying a loss of 0, penalty of 0. But take the case of these two points, blue points that lie below the decision boundary. Their true label is +1, but their prediction is negative because they are on the same side as the red points, which means the product of y times the score is going to be negative, and they're paying a penalty of +1. So that is exactly what the loss function is doing. Every time a sample makes a mistake, it's making the function pay, the model function pay a penalty of 1. And for all those where there are no mistakes, they make it makes the function pay no penalty. So it's roughly just counting the number of mistakes it's making, the model is making on the training data, the fraction of the sample where it's getting it wrong. But then, like we discussed, this is a loss function that is not easy to optimize. It is not a, a loss function that can be where you can solve for the parameters W easily to find the optimal or the best model F star. And hence they have numerous approximations of this where they smoothen out this step, and depending on the kind of approximation, you have various kind of smoothings, and these are the various loss functions that you get. Now that you have uh, the uh, the loss determined, what kind of model should you use? Uh, take the simple example where you have training data of black dots or black points. And there are two models that you see. One is the straight line x equal to y, and the other is the high dimensional polynomial that literally passes through each of these black dots, or it's passing through each and every one of those points in the training data. Now, if you have a test data point, like you see in the red dot here, which of these models would make a bigger error? Well, here it turns out that the high dimensional polynomial that we are fitting, which has zero training error, because if you make a prediction on any of these data points, the black dot points that are part of the training data, you make a prediction, as in you apply your function, this high dimensional polynomial function for any of these data points, and it will make a zero error. So it has a zero error on the training data, and yet it has a higher error than the simpler x equal to y line on the test data point. So this is an example of overfitting. It's a case where your model, the high dimensional polynomial model, is too complex for your data. What's happening is that it's not just fitting to the pattern in your data, but it is also fitting to the noise that's coming with it. It's fitting to the randomness that's coming with the patterns. And this is not a good thing. So overfitting is not a good thing. You don't want to fit to the noise. You just want to fit to the pattern in the data. So you should ensure that your model is not too complex for the data that you're operating on. Now, what happens if you have the opposite case where your data is a high dimensional, in this case, uh, something coming out of order 2 curve, but the model that you're fitting is not sufficiently complex. Now the opposite happens. You continue to make errors because the model that you're fitting is not complex enough to capture the target distribution. So it is important to ensure that your model is a right fit. It is neither overfitting nor underfitting. But how do you do that? In the case of linear models, you would do it with something called regularization. And what regularization really does is it adds a penalty on the complexity of the model that you're fitting. Your model is parameterized by parameters W, and you would add a penalty on the parameters W, a function of your parameters W as a penalty, with a parameter, an additional parameter lambda that you control uh, to ensure your model has the right complexity. Take as example, the L1 norm, which is simply sum of absolute values in the vector. That's one kind of penalty that you could add. It gives you algorithms very similar, results very similar to the lasso algorithm. What it really does is it tries to push uh, small and you know, uh, small and insignificant coefficient values to zero. So what it's trying to do in terms of the feature variables is that it's telling you that certain features are not very useful in prediction, so don't use them in determining or in making a decision. That's what your L1 regularization does, and L2 does something a bit different. It's not as aggressive as the L1 regularization. It won't force them to zero, but it kind of does a uniform reduction in coefficients in all your coefficients involved. And by choosing an appropriate lambda, you can ensure that your model has the right complexity. It's neither overfitting or underfitting. So regularization is what you would use uh, to ensure you're fitting right and not overfitting or underfitting. Right, but how do you quantify a poor fit? What are the variables that you would use to determine uh, whether a particular fit is a good fit or a bad fit? Let's say we have 1,000,000 data samples in your training data, and build a model M1 by drawing a random sample of 200 instances from the 1,000,000 samples that you have, and learning a model on top of this 200,000 samples. So you're just sampling 200K uniformly and randomly from the 1,000,000 samples that you have, and you're fitting a model to it, a linear model, just like we have seen. You determine the uh, predictor function. Let's say it's a linear function f, and you determine the loss function. Let's say it's a square loss. Let's say you're using regression, it's a square loss. And you fit a model. So you get a model M1 or a model F1, let's say. Now repeat this process. Draw another sample of 200,000 from this 1,000,000 and fit another model F2. Repeat this 10 times and you get 10 different models F1 to F10. Now, let's say you receive an unseen input, a new input that is not part of your 1,000,000. It's a test input. It's a new input that you get. And you have to make a prediction on this input. Use your 10 models to make 10 different estimates of the value of the prediction. Okay, so you have got 10 different estimates from your 10 models on this unseen sample. What are the various ways in which these 10 predictions or 10 estimates can look like? The best case is you have these 10 estimates very neatly and tightly clustered together, and they are very close to the ground truth, which is the true value that you're trying to estimate. These concentric circles that you see, they are the distance from ground truth. At the center of these circles is the truth, and these crosses that you see are the estimates from your 10 different models. And what you see at the left bottom is the best case scenario. Each of your estimates is very close to the truth, and all your estimates are tightly clustered together. That's really the best that can happen. So you have what is called low variance, which is the spread uh, in your estimates, and low bias, which is how far you are from the truth. Now, what is the worst that can happen? It's the right top. They are really spread out very far. Your estimates are very far from each other. That's high variance. And they're all far from truth. That's high bias. And what are the other two scenarios? You have low variance. They're all tightly together, but it's got a high bias. You're far from the truth. And the other case, of course, is you have very high variance, but you have low bias, which is to say, they're all spread out, but they're spread out around the true value. Now, your overfitting and underfitting are really just cases where you have high variance and uh, high bias. So overfitting is where you have very high variance because like you've seen in the high polynomial that we have fit to uh, uh, linear data drawn with some random noise added to a linear function. You're fitting even to the noise, and hence you cause high variance there. On the other hand, underfitting is where you fit a model with complexity lower than necessary. So it always has a problem of very high bias. So these are the two important statistical components that you would use to determine whether your fit is good or bad. While these are the statistical quantities that you would use, you cannot always compute these in practice. So how would you determine in practice if a particular fit is a good fit or a bad fit? And this is how you would really do it. Given any data set, you would split it into training sample and test sample. And these are distinct samples. So none of the records or instances from your test sample would appear in your training sample. They are distinct samples. And in training the model, which is in learning your model F star, you would only use the training sample. You should never use the test sample. You train on the training sample, learn a model, and then use the performance of this model on the test sample to determine if it is good enough or not. So this green curve that you see is the error on the training sample. And the prediction error is a function of the bias and the variance. If you have very high bias and very high variance, you're going to make a big error. You want both bias and variance to be low. But when that is not possible, you trade off one for another and ensure that your test error is as low as possible. And this is why you should split your data into train and test and ensure none of your test samples appear in your train, and monitor the prediction error that you're making on your test sample to see what is the right complexity of the model that will give you the best generalization. So in the case of the high dimensional polynomial and x equal to y that we fit to the data points, uh, x equal to y uh, is a simpler model, a model with lower complexity compared to the high complexity model of high dimensional polynomial. Now, what is happening with the high dimensional polynomial is that it achieves a very low training error. It literally achieves a training error of 0 because it's passing through each and every one of those training data points. But its test sample is pretty high. So you want to avoid having this scenario where it does not generalize to unseen distribution, but it's also fitting to the noise along with the patterns in your training data. And you also want to avoid the case where you're underfitting, like we have seen in the example where data comes from a higher degree curve, but we are fitting a linear line there. So the right thing to do is generate train and test samples correctly. And as you fit models of different complexity, plot both the training error, which is error on the train sample, and the prediction error on the test sample. And pick that model where the error on the test sample is the lowest. So it is error on the test sample that gives you that serves as an indicator of how good the fit is. And that is the one that's going to help you generalize to unseen data. This is very important, and this point is going to recur in subsequent lectures as well. And broadly, simple models with small number of parameters have high bias and low variance. You want to ensure you want to increase the model complexity in such cases. On the other hand, if you have very complex models with large number of parameters, you're going to have low bias and high variance, and you want to do the opposite there. You want to regularize more aggressively, maybe use feature selection, maybe when increase the amount of training data if that's possible, and so on. Right. So the broad takeaways here is that you choose the suitable predictor and loss function, the constituents of the learning algorithm, and make sure you evaluate the model fit to ensure generalization. And you do that by tracking train and test errors. Now we will look at some linear models. The simplest is the linear regression model. It is linear, so the predictor, like the name says, is a linear function of the feature variables. It's W transpose X, just like we have seen in the age income example. The loss is a squared loss, the true value minus predicted value squared. And this is what we would sum over all the data points in the training data and minimize. How would we solve for it? In this particular case, it's a convex function, which means the objective function, this whole function that's inside the parenthesis is the objective function. It's called it's a convex function in this case, which means that if you can find the global, if you can find any minimizer of this function, it is going to be the global minimum. Or to put it another way, if you can find a point in the parameter space where the derivative of the function is 0, that is sufficient to say it's going to be the global minima of this function. No, there are no such things as saddle points and stuff for convex functions. And for linear regression, you can compute the derivative, set it to 0, and solve it analytically, and you will get this. This is something you can compute in closed form. Not always, because You'll have computational issues because of this inversion, particularly if you have very high dimensional feature spaces. But in theory, this is the solution. What if you have to add some regularization? So this is L2 regularization, the Euclidean norm on the parameters. You can continue to use the same solution, but with a small modification. Before inversion, you offset the diagonal elements by a value lambda, and the rest of it works normally. Now we can extend this to logistic regression, which is really a method that applies for classification. The linear predictor continues to be the same. It's W transpose X, but the loss function is going to be a bit different. What we have here is a variable y that belongs to one of these two classes, -1 or +1. It's a binary classification problem. We are going to compute the probability that the sample xi belongs to the class yi. So we need a function that will give us the probability that the sample xi belongs to the class yi. And this is where we use the sigmoid function, which is nothing but 1/1 plus e power true value times the predicted score f of x. Now that we have the probability of the sample xi taking the belonging to the class yi, we can compute what is called the likelihood of the data, which is nothing but the product of the probabilities over all the samples in the data set. While in theory, computing the product over all the probabilities is fine. In practice, it's going to cause a lot of numerical underflow issues. So rather than taking the product of probabilities, we take sum over log of probabilities. It's the same thing. It's just that we're taking a logarithm. Now we take sum over log of probabilities over the data set. And this is what is called the conditional log likelihood. It's conditional because we're taking probability of class label given the instance. This is what we want to maximize because it's probability that this data sample would have occurred given that my model's parameters are W. And that is what we want to maximize because that is the sample that we have observed. To fit it into our argmin loss framework, we just negate this, and then it becomes a loss function like we have seen so far. And then the rest of it works. It fits into the familiar equation. We minimize and find the best set of parameters. Minimize this negative of log probabilities over the full data set. And we can also add a regularization as necessary to find the right fit. If we were to find the right W star, then at inference time, we would take this probability of the test sample. And if it is above 0.5, it belongs to class 1, otherwise it belongs to -1. However, unlike linear regression, we cannot solve this analytically. We can compute the derivative, but setting it to 0, the equation is not something we can, it's analytically intractable. That's not something we can do like in the linear regression case. So how can we solve for the optimal parameters or the optimal model when it is not analytically tractable. Let's squash the whole uh, term inside the parenthesis into an objective function j. It's a function of the data and the parameters, but the optimization happens only on the parameters w, right? Uh, the trick that they use here is they start with some estimate of the parameter w0 and then move in a direction where the value of the objective function j goes down. And how do they find this direction? They compute the gradient at w0 and move in the opposite direction. So the gradient is the direction along which the value of the function goes up. So we just move in the direction opposite to the gradient for the value of the function to go down. So this is the trick that is iteratively used until some termination condition is met. So the equation looks like this. Uh, wk plus 1 is nothing but wk minus del j. This nabla j is nothing but the gradient computed at wk. This eta here is the learning rate, because we don't want to overshoot and go past the minimum. And the termination condition is if the gradients are too small, we know that we are very close to the minimum, or the consecutive steps are very close. We know that we are either too close to the minimum, or it requires tweaking the learning rate, because even if the learning rate is very small, the consecutive steps could get very small. So it's important to use a suitable learning rate scheduler for good convergence. While this is what gradient descent is, and it's the workhouse over which a lot of algorithms run. If you have a very large data set, your training data is really large, it has, let's say, hundreds of millions of samples, this function can be very expensive to compute. So what they have done is, rather than compute this full gradient, they said, can I get an estimate of the gradient? Because all I need is one suitable direction in which to move. And if all we need is an estimate, rather than take all the data set, why not plug in just one sample? And that is exactly what stochastic gradient descent does. It replaces the data by just one sample. And then the rest of the equation is the same. But the problem with this is that there is too much variance. So the right thing to do is something in between, not the full data set, not just one sample. Use a small batch of samples. The larger the batch, the better is the estimate. Then after a point, if the batch is too big, it's going to be very expensive to compute. So there has to be a balance on the number of samples B that we use in the batch. So the equation update equation is essentially just the same. It's about how many samples we are using here to compute that estimate of the gradient. There are then, of course, specific implementations of this that you will see, like RMS prop, Adam, Adagrad, and so on, with their details. You'll see them in later lectures. The broad summary connecting this to what we have seen in a very early slide is this. The training procedure requires collecting appropriate observations from which the learning algorithm is going to learn the mapping from inputs to outputs F, which is what we will use at inference time. And this requires us to gather the data, the right data set, choose a model F that we want to fit, choose a loss function that will determine how good the models are with an appropriate regularization if necessary, and then use an iterative solver uh, on this objective function, which is a function of the training data sample and the predictor and its parameters. And then we get the optimal parameters. And this function with the optimal parameters is what we are going to use at inference time to make predictions on unseen or test samples. We must pay careful attention to generalization, which is what we track through the train and test samples. And the training loop looks like this. We draw, this is the batch gradient descent that we've seen. We draw a sample from our training data, and we run this update function on the parameters until we hit termination, and then return the final set of parameters, optimal set of parameters. So that the summary is we find suitable loss and predictor, and an appropriate optimizer, and solve for the optimal parameters, paying careful attention to generalization, and use the final model for inference. Thank you so much. If you have any questions, please note them down for the Q&A session, and we can discuss them there. Thank you so much. Bye.
Okay, hi everyone. This is Abhishek. I'm an applied scientist here at the International Machine Learning Department. I am going to be taking the next module on tree-based models, within which we'll be talking about the decision tree and also ensembles of trees, bagging models and boosting models. That'll include like the random forest, various things such as ARA boost and gradient boosting. So let's go back to this 360-degree view. You can see that these are the topics we'll be covering in the supervised learning module. So let's just jump right into it. So decision trees. So what is a decision? That is derived from the training data. So we'll see an illustration right over here. So suppose this is my training data. I have, and this is taken from the very famous Kaggle Titanic dataset. You can see over here I have 10 rows, and I have various features for each row. I have the P class, which is the ticket class. So this person was in third class, this person was in the first class seat, so on and so forth. The gender of the passenger, the age of the passenger, the fare, how much they paid for the ticket. This isn't the same, as you can see, between even in the same class, like third class, this person paid 7.3, this person paid 8.1. It might be depending on how soon before the ship left that it was actually that they had to pay more. And this is my target variable. So all of these are my features, and this one is my target, whether the passenger survived or not. So we're trying to use all of these features to predict my target, right? And we're going to be building a bunch of rules, a collection. You can imagine a very big if-else statement, which is called a decision tree. And here it is on the right. So imagine this is the tree we've already finished building. So what is happening over here? It's saying that, okay, I want to now predict if somebody has survived or not. I want to predict a 0-1 label, or over here, green means they've survived and red means I'll predict they've not survived. And how will I do it? So first, given a new example, suppose somebody comes in who has same characteristics as this ID number 2 person. So it'll first look at the gender. It'll see, okay, this person was a male or not a male, right? Male or female. So if it is male, then it'll see, is the person's ticket class, the passenger class, is it less than 2.5? Meaning that, is it basically 1 or 2? And if so, if it is yes, then it will predict it has survived. And if it is no, then if it is a passenger class C, you say the person has not survived. So what is this saying? This is saying that our model has learned to predict that when the passenger is a male and when they have ticket class 1 or 2, they have survived. But when they have ticket class 3, they have not survived. Right? So this is the decision tree which is learned. And you can follow the same logic to derive how passengers will be classified on the right hand side of this tree. Right? Over here it's basically saying only women who have passenger class 1, only they have survived. The others, it's saying that neither of them have actually survived, because both of them are being marked as red over here. So there's over here we've had an example of a simple decision tree. It only has 2 levels. It's only using 2 different features. Right at the top, it uses the gender feature, and you'll have to notice that after it's made a decision based on gender, it can't make another decision based on gender. Right? It has to choose a different attribute to make a decision based on. Over here, we've seen a classification tree where the leaf nodes are associated with a class label or class probability. We also have regression trees where you can basically say, suppose instead of having to predict whether the person survived or not, suppose my my target was actually that, okay, what is the age of the person? It's a regression problem. It's one which gives out a number instead of a class, right? So in those situations, a regression tree, the leaf values are associated with numeric values and not like a class label like true or false. So let's talk about a bit about what a decision tree is doing. How is a decision tree kind of splitting our input space? And over here you've seen this is a different tree, and I have 2 variables over here. Variables are similar to my attributes, like p class, sex, age, fair, etc. Over here they're called x and y, but you can imagine they're called x1 and x2 as well. And you're seeing what the decision tree is doing. This is the classification tree. Every time it has 3 leaves over here. So you can see this one, and this one. And these 3 leaves correspond to different regions of the space. So if you can see over here, this rule x less than 3 has put up this one big partition in between the space and divided in 2 parts, this side and this side. Now under the ones where x is less than 3, so on this side, there's another partition rule which has been put up, which is saying that y is less than 2. Y, again, remember over here is like x1, x2, So y less than 2, that means this is one other partition that's been come up between, like even within the partition of x less than 3. So now this part has been partitioned. And so you can see over here, when y is less than 2, it's done a perfect split of this data. All of the red points are in this side, and all of the blue crosses are in this side. And this is exactly what we want. We want this kind of really perfect splitting, because it means that the remaining, the area in which is there post splitting, it's very pure. It has a very high, it's not mixed. If you can see on the side of x greater than 3, 5 instances are red, 7 instances are blue. It's mixed, it's not a very clean split. You can probably say that, okay, if I had used the y and done like a y greater than 2.5, another rule over here, it would have made an even better split, and that's right. So, but over here we've not done that. There's no real reason for it. It's just that this is how the tree was built. So now we are able to get these 3 big regions over here. This one, and this one. And they correspond to our 3 leaves. And this is what a decision tree really does. It takes your data, it takes the points as they are, and it splits them into multiple different regions according to the rules which have been set up. And though each of those regions makes a single prediction. So over here, it's going to make the prediction that whenever you find a new example, we find it comes between 0 to 3 on the x axis and 0 to 2 on the y axis. If it comes in this region, you're always going to predict that it is a blue x. If it comes into between 0 to 3 and 2 to 5 or 2 or basically above 2, any number above 2, then we're always going to predict that it's a red dot, right? What about this region? Over here it's a bit mixed because we don't have a very clear split, but we see that in this node over here in this leaf, 7 of them are in the blue X and 5 of them are in the red dot. And so we are going to predict the majority class over here. We're going to predict that it's anything falling into this region, any new example, they're going to predict that it is a blue X because that is the majority vote of this region. So like I said, decision trees break the input space into regions where all the points in one region make up the predicted value for that region. And in regression trees, this is a classification tree. If we have a regression tree, we take the average values of all the points falling into this. So over there we wouldn't have this sort of dots and x's. We would just have a numeric value associated with each data point, and we would take the average value and predict that as the output for any new data point which is falling in that particular region. So we'll take like the average of all of these for this region number 1, the average of all of these if it falls into region number 2, the average of all of these if it falls into region number 3. So now that we have an idea of what a decision tree does and how it actually divides the space into multiple regions, let's talk about how you actually go about building such a decision tree from the raw data points. So the algorithm you follow is a recursive partitioning algorithm. Essentially what that means is that at every point you do the same thing. For every node you do the same procedure. And the procedure is you see what are all the attributes available to me which I have not already used to split so far, and you say, okay, from all of these, which one is giving me the best split criteria? That is the one which leads to the greatest decrease in the impurity of the resulting two nodes, right? So let's say that the attribute which gives the best split criteria is x1, and the best split criteria, that is the value of that attribute, is s1. So what we do is, once we've selected this best split criteria from all of the criteria available, we push all the training examples into the left nodes or right nodes based on their value of this attribute. If all the training, if a particular training example, the value of the attribute x1 is less than the value of s1, then it goes to the left, otherwise it goes into the right node, right? Then, so now what we've done is we've taken our population and we have split it into two parts. Then for each of those parts, we do the same thing with the remaining attributes. And that way we continuously and recursively build our tree. So it's a greedy divide and conquer algorithm. So let's look at what are the different kinds of split criteria you might have. So let's say for this data set over here, we want to split based on the, we want to build the very first node for this decision tree on this data set, right? So we have a variety of split criteria available to us. We can have gender as one split criteria, can be male or female. So x1 will be gender, s can be male or female. We can also use age as a criteria. For example, it might be that all of the ages between 1 and 80 could be valid split criteria, and as you can see over here, it'll give us two nodes. It'll give us all of those the population where the age is less than that value and the one where the age is greater than that value, right? We can also have the ticket. We can say, okay, the ticket is either 1 or it's not 1, so it's 2 or 3, right? This will be like the way we are splitting it. So now out of these, and each of these are different split criteria. Each of these, orange and green boxes, each of these pairs is a new different split criteria. So we want to choose the best one. We want to choose the one with the greatest, which leads to the greatest decrease in the impurity of the resulting nodes, right? So let's look at an example of this first before we talk about what are the criteria for measuring impurity of nodes. So we've taken over here two different examples. One is we are splitting on this age criteria. So we're using age of less than 20 as the splitting criteria, and one we're using the gender, male or female. So this is our initial data set of all the different examples. As you can see, there's over 600 and almost over 700 of them. And now based on age, we're splitting it into two parts over here, and over here based on gender, we're splitting it into two parts. Now which one of these two splits is better? That is determined by measuring the node impurity. And over here we've used the sorry. Over here we've used the Gini impurity criteria, and you can see we'll explain what is Gini impurity in the next slide. But over here you can see that the Gini impurity of this node, where age is less than 20, is 0.49. The one of this node, which is age greater than 20, is 0.47. And the weighted average of these, where you take the weights as being, what is the fraction of the total falling into this. So it's basically, 72 plus 85 divided by the total of this, right? That is the weight. You multiply that by the Gini impurity value of this node. You take the fraction over here, which is 339 plus 211 divided by the sum of this. You multiply that by the fraction, the Gini value over here, and the sum of those two fractions gives you the weighted average. So you calculate the weighted average using this split criteria, and this is your Gini weighted average. This is your Gini impurity basically on using age less than 20 as your splitting criteria, right? And a similar thing you do over here using the sex as either male or female, right? So basically sex is equal to male is your splitting criteria. And very similar process, you calculate the Gini of this node, the Gini of this node, you take the weighted average, and you find that as 0.34 over here. And as we see over here, 0.34 is less than 0.49. So then this is actually a better split. So that's how we look at all the different splitting criteria. We get what is the weighted Gini impurity of each of them, and we choose the one with the lowest Gini impurity value. And that becomes our best split criteria. So now let's talk a little bit about what is your Gini impurity value. What is this idea of Gini impurity? So the idea is that for a particular node, now what we've done is we've selected some splitting criteria and we moved it into the left and right subtree. So we're taking the node in, let's say, the right subtree, right? For that node, we have to calculate the Gini impurity value, and that is calculated using 1 minus the square of the fraction of each class, of the examples falling into each class, right? And we sum up that over all classes. So to go back to this example over here, we can see in this tree the fraction of examples falling into class number 0 is 64 divided by 64 plus 195, right? So we take that and we square it, and then we also take the fraction of examples falling into class number 1, which is 195 divided by 64 plus 195. We square that, right? And we do 1 minus both of those squared terms, and we get our Gini impurity value. That becomes the impurity value for the node. And as you can see, the Gini impurity value, it's a interesting thing. It takes values between 0 and m minus 1 divided by m, where m over here is the total number of classes. We've done in our example with 2 classes, you can have multiple classes. The maximum value is, the maximum impurity is when your node is exactly divided half-half, in a binary case. So if right now over here you see the division is not equal, label 1 has many more, so we're tending to lean towards label 1, so the Gini impurity is maximum when this is exactly equal. If both of them were 100 or something like that, then the Gini impurity would take the maximum value of 0.5 in the binary case. And remember that the high Gini impurity value is bad, we don't want it. The ideal case is, this splitting criteria is perfectly able to split a dataset in such a way that all of the examples in this have the same label, all of the examples in this have the opposite label. That is our ideal case. And in that case, the Gini impurity of both of these nodes would have been 0. So Gini is this criteria, and it's basically a criteria which is used to measure the impurity of each node. Another similar criteria which looks very similar in terms of the graph over here is entropy, which is a little bit more general, and it measures very sort of similar thing. It's just a way to determine what is the impurity of the node which you have. This is used to, like I mentioned before, determine, okay, how do I actually split these, and which is the best split. So these are for classification trees. For regression trees, you can use a square deviation, which is basically you take the each value, you subtract the mean, you square it, and you calculate this. This is basically your mean squared, your squared error, right? And you do this for each node very similarly to how you calculate your Gini impurity. So now that we've used this criteria, and as you can see, you can recursively start from the root, and you can keep on splitting it. You can split this further into other nodes. You can keep on splitting it. The question is, when do you actually stop? When should you stop, and at what depth should you stop, right? And the question is, should you even stop at all, right? The answer is that yes, you should actually stop, and a smaller tree is better. Basically, the deeper the tree is, the higher the chance that you have overfitting. And that is because the regions, as they become smaller and smaller and smaller, you have fewer and fewer data points in that. And so it becomes very noisy. It becomes very high variance. And as a result, what happens is that if you have only, like for example, in this node you have only 2 samples which are being used to determine whether it is a positive or negative class, that's not enough. Like the others have 100 samples or 70 samples. That's a lot better. But only 2 samples is just not enough. And so you tend to overfit to the data. Just those 2 points might be positive, and so you'll say it's positive. But in reality, it could be that it should be negative, right? So the way to overcome this overfitting issue is to use decision tree pruning, where essentially you say, okay, I've built this big tree, I'm going to take a step back and I'm going to cut off the nodes which are below some certain threshold of Gini impurity, for that splitting criteria. I'm going to remove a few of them, right? And then that just removes the non-critical subtrees. That is the one which have the least impurity reduction or information gain, and this leaves you with a smaller, simpler tree which is less prone to overfitting. So now that we've learned how to build a decision tree, let's think about how decision trees are used in the real world. Very often a single decision tree, it's a model which has a very low bias because it makes almost no assumptions about how the data is. It doesn't, like a linear regression model, it makes the assumption that the data is actually linear. The true function, the true the nature given function is actually a linear model. But a decision tree makes no such assumptions. It just looks at the data and creates rules. So it's a very low bias model, but it's also a very high variance model. As we explained, when the regions are very small, the created regions are very small and only contain very few data points, the prediction can fluctuate a lot. So just getting a slightly different data can completely change how the tree looks, and so it's a very high variance model. So trees, decision trees on them by themselves are not very widely used, but what is very common to use are ensembles of trees. An ensemble is basically just a collection of different models trained on different data, which we are going to use together and combine to make a single prediction, right? And the reason for this is that ensembles can either reduce the variance, or they can reduce the bias. And if you remember from this bias variance trade-off diagram that you had seen earlier, you want both low variance and low bias, and that will give you a very good accurate prediction, which has both low training error and low test error. So what are the different techniques which are used to ensemble decision trees? We'll discuss two of them in this particular module. The first is the bagging approach, where you have an ensemble technique where you take multiple bootstraps. We'll explain what that is in a minute. You take multiple bootstraps of the training data and you create multiple models, each of them having low bias and high variance, and then you take the average prediction of those models, or you take the majority vote if you're doing classification, and the resulting model has a low variance due to the aggregation of all these models. This is the bagging approach. The boosting approach is one where an ensemble is learned iteratively. So basically you train one model, you look at it, you then learn to train another model based on the errors that the first model made. And so to reduce those errors, you train another model. Then based on the errors the first two models made, you train a third model, and so on and so forth. And we'll be looking at two different kinds of boosting methods. The first of which is auto boost, and the second of which is gradient boosting. So let's go into the bagging approach right now. So first, bagging stands for bootstrap aggregation, and the bootstrap it's a general statistical tool. Actually, you can use it even outside of machine learning just for data analysis. What it does essentially is that you start with an original data set, and you and suppose your data set has m data points, right? You resample your data set essentially, meaning for each data point you uniformly just pick it with replacement, and you create a new data set which has again m data points, and with replacement meaning that some of the data points might be repeated. So if you see over here, right, this is our original data set z, and my z star 1 is my new data set, where I have these the first row and the third row are just repeats. They're picked from this row in the original, right? And even over here in my data set, I have the second row and the first row are repeats of this point number 2, right? So like this, each of these is called a bootstrap. So you create multiple bootstrap samples of your original data, right? This is the very first step in bagging. Then on each of these you train a model, and finally you just aggregate their results. You just take when you're making a prediction from the final model, you just take the input example, you pass it through all the models trained on each of these data sets, and then that becomes and then you average the predictions from all of those models, and that becomes your final prediction, right? That's for regression. In classification case, you take the majority vote from all the models trained, and that becomes your final prediction, right? Now, why is this something which actually works? What does this make, like, why is this used? And the reason is that the final model, which is the aggregation of all of these bagged models, it has lower variance, you know, than each of the individual models. And that's because you're averaging the outputs of multiple uncorrelated quantities. And that, can be proved is something which reduces variance, right? Now, this is very good for a decision tree because, as you've said, a decision tree is a model with low bias and high variance. And so we are actually going to get a model which is having low variance as well. And you can use bagged decision trees just on their own, but a very powerful model which is actually very frequently used is the random forest, where you do essentially exactly this same process of bagging, but you take one additional step. So just to remind you, what happens is that you start with a training data set, you break it up into multiple bootstrap samples, meaning each bootstrap sample is you just take the data set and you resample it again. You pick each of the data points at random and you create a new data set with the same size as the original. And you do this, over here you can see it's been done 3 times, right? So you create B bootstrap samples, and the idea of this is that it increases diversity. Then on each of them you train a random decision tree. A random decision tree is one where you select a random subset of the attributes for each of the sample, and then you train a normal decision tree algorithm and you build a decision tree based on that, right? And the reason for selecting a random subset is that it reduces the correlation between the trees which are created at the end, And then the prediction is exactly the same as normal. You combine the outputs of the various trees which you've created by either averaging, if you're doing regression, or if you're doing classification, you take the majority vote. And this leads to a model with very high, with very low variance. And you can keep on endlessly sort of doing this. You can keep on building trees. You can keep on building almost as many trees, and the variance keeps going down. After the point, it does, saturate. If training 100 different, creating 100 different bootstraps and creating 100 different trees is not very different from creating 1,000 bootstraps and 1,000 trees. Your end result is the predictions are not going to change too much between that, but they're all going to be very low bias and low variance predictions. So the random forest model, it's a very fast, very efficient model because creating each decision tree is quite a quick procedure, and it has low bias and low variance, right? So now that we've discussed bagging and the random forest, let's go on to boosting. Boosting is a different way of ensembling models, and it's basically building a combination in an iterative way. In bagging, you could train each of the trees in parallel because they were completely unrelated to each other. But over here, one tree is built based on the outputs of the previous tree and what sort of errors it makes. And the idea is to iteratively sort of keep on building a combined model where the error keeps on reducing and reducing and reducing, right? So the main idea in boosting is to start with what's called weak learners, which could just be like a very simple heuristic rule, So to give an example, let's say you have a weak learner, which is a decision tree with just a single node, just a single decision rule. Now that is, obviously not a very good tree, but obviously it's very fast to create. And the idea, and it'll have some accuracy. The accuracy will not be amazing, but the accuracy will probably be better than 0.5, right? Because it has learned some rule to at least classify things into 2 directions, into true or false correctly. So the idea is this is a very high, each weak learner is a very high bias model, right? A single decision stump, what is called, with just the root node, it's a very high bias model. And so we are going to combine a lot of these high bias model using a procedure which reduces the overall model bias, and that is boosting. Over here, we have presented one of the most famous boosting algorithms, and the first rel boosting algorithm called ADA boost, and it proceeds as follows. The algorithm: you start with the training set, x1 y1 pairs. You can imagine this to be a classification problem where y is true or false, and then you start with a weak learner, which can be like a decision stump, right? Just a decision tree with a single node. You proceed in a number of rounds, in t rounds. What you do is you initialize a vector at the very start, at the very first round. You initialize a vector which is it's a probability vector, so it's going to have probability values first, all of them being 1 upon m, and there's m of these values, right? M here is your number of data points. So you have a vector where you have a equal probability at the start for each data point, and then in each iteration of ADA boost, you create a new weak learning model. From the weak learner, you create this model, and the procedure to create this model is over here. So basically what you do is you create a new version of the training data by resampling the data points in your original training data based on this probability vector d of t, right? So d of t to start with is a uniform vector. So suppose there's 5 data points, it'll be 1 by 5, 1 by 5, 1 by 5, 1 by 5, and you are going to resample, or rather basically you're going to create a new data set of 5 data points by resampling each data point based on this probability. So in the very first iteration, since all the probabilities are equal, you'll end up with something which looks similar to the original data set, but it won't be exactly the same. You could have repeats, for example. So that way you are creating this new data set S prime, and you train your weak learner on S prime. Over here there's a typo, it should be S prime. You train your weak learner on S prime, and you get this model over here, H of t, right? Now H of t, it's a model which has some accuracy. It's trained on a resample version of the training data. It has some accuracy, right? So you compute epsilon t, which is the weighted sum of all the errors made on the training data by this model. So it says what this does, this equation, what is essentially doing is essentially you're saying, okay, using the model I have just trained, I'm going to predict on all of my training samples again and get predictions htx of 1, htx of 2, etc, etc, right? Those are all of my predictions. I'm going to see where it does not match my ground truth, where it is different from my true label y, right? And all the ones where it is different from my true label y, I'm going to pick them, all of those examples, and I'm going to pick the associated weight, probability weight of those examples, and I'm going to sum it up, and that gives me this term ET. This is my error term. So now I've got this cumulative error term, and if my predictor is perfect, then this error term will be 0. If my predictor is horrible, my error term will be 1, right? If my H of t, which is created, the model is completely incorrect, then my error term will be 1, right? And but typically it has, the idea is that your the weak learning algorithm WL, it's going to create something which is not perfect, but it's not absolutely terrible also, right? Now once you've got this error term, use that to calculate the weight of your classifier HT, right, which is calculated using this formula. So that is WT, the weight of the classifier in the final combined model, right? Then the final step in the ADA boost procedure is that you update the probability scores for each example in the dataset, right? And you update it as follows. You take the exponential of the negative of this weight, you multiply it by the label, so this is like a 0 or 1 label, uh, you take the prediction and you multiply that with the true label. So this is basically something which will give you a value which is either 0 or 1. Over here the labels are +1 and -1, so it'll give you either +1 or -1 over here, right? It'll give you +1 if the prediction is correct and -1 if the prediction is incorrect, and you multiply that by the existing probability score, and you then just you do this for each of the probability scores. So there's m data points, probability scores. You multiply each of them by this term, and then you just take the sum of them, and then you divide each of the probability scores weighted by that term. So basically that way you get the new value of your probability score, right? And this is basically going to only so this is going to only actually this is going what is this doing, right? This whole computation is going to upweigh the probability scores of those examples which have been incorrectly predicted by this classifier h of t, right? Whenever these two are different, right, then it will give -1, and so this is going to become a high positive value. It's going to be wt into some positive exponent value, so it's going to become a very large value, and so it's going to upweigh basically the probability score of that value, and therefore it's going to upweigh the cost that the next round, if the classifier incorrectly predicts that, it's going to pay a very high cost, right? So this is the idea of these probability scores d of t1. They are determining, okay, what is the cost going to be for misclassifying, for building a model which misclassifies a particular example, and it's like a vector. So for each one there's a different score. And the idea of AdaBoost is that you keep on focusing on the examples where you are making mistakes. If you continuously keep on making mistakes on the same example over the course of multiple rounds, that example is going to get a very, very, very high score, right? And the idea is that you have to bring down the total amount of error iteratively this way. So finally, suppose you've done this whole process, you've completed t rounds, and you've gotten t versions of this classifier and t corresponding weights. The final hypothesis is the final output model is just going to be a simple combination of those. You take each model from the weak learner at each round, you multiply it by the respective weight which was calculated on the training set, and you just sum those up. This will give you a value which you pass to the sign function. The sign function is just, if it's positive, it gives +1. If it's negative, it gives -1. If it's 0, it gives 0. Or arbitrarily, it can give +1 or -1. So this is the overall AdaBoost procedure. What is happening is that you are over time iteratively adding one more model, and you are actually reducing the training error. You can prove mathematically that the training error of the combined model, as the number of rounds increases, the training error decreases exponentially fast. So if you have 2 rounds versus if you have 10 rounds, in 10 rounds it's going to be exponentially much lower than 2 rounds. So this is the overall AdaBoost procedure. And the real beauty of this algorithm is that you can start with really stupid classifiers. You can start with the weak learner just as being a decision stump, a decision tree with a single just a single decision rule, and to classify only a depth of 1 basically. And you can still end up with a final model which has very low bias and is actually a very good predictor. It has very low training error. And that's the real beauty of AdaBoost. It's got a lot of very nice theoretical properties, and the inventors of this algorithm, Robert Chabaya and Laurent Fjord, they both won several awards for this algorithm. So here let's just take a toy example and see exactly how this works, right? So here's the very first iteration of this. And in round number 1, you've built a single classifier, and you've upgraded the classifier. As you can see, has made these examples over here are incorrectly classified by the classifier h1, and so you've got a very high in the next round, the value of d, the probability score of these examples, is much higher, and of the other ones is much lower, and you can see that these all have been shrunk, right? So in round number 2, you have a second classifier which is now incorrectly predicting these ones, and over here then these ones are given a higher weightage in the next round. Round number 3, these ones are given a higher weightage, and so on and so forth. And so over here, after 3 rounds, you've built 3 different classifiers, and these are all, like I said, a single rule, right? So it's just a single rule which is dividing, which is saying maybe x less than 5, and over here x less than 10, and over here y less than 3 or something like that. So very simple classifiers. The combination of them, it ends up with this very nice classifier over here, which in the end is able to make a very high quality prediction. And so you're able to get a final model which is very low bias, and it has high training accuracy as well. And usually this is a model which also generalizes well and does well on the test data set as well. So now let's get on to a different way of doing the boosting procedure, and we'll talk about gradient boosting, which is an extension of the ADA boost algorithm in a way which might not seem very straightforward, because it uses gradient descent in a space of functions rather than doing it in a space of data as you're normally associated with in linear regression and logistic regression. So before we get into the details of it, let's suppose you want to play a very quick game, right? You're given the data set, s is equal to x1 y1 x2 y2 up till xm ym. So you have m data points. Your input x is some vector, and your output y are real valued. So this is a regression problem. Your task is to fit a model to minimize the square loss. Remember, the square loss is the model prediction minus the actual, the sum of the square of that, the sum of that over all data points. That is your squared loss, right? Now, to solve this problem, suppose your friend wants to help and they give you a starting model f. You see the model's outputs and you see that it is good. It has a low square loss, but it's not perfect. So how do you actually improve this model, right? You're not allowed to change the model your friend gave you at all, but you can add a new model g to the output, such that you are, instead of predicting f of x, you're predicting f of x plus g of x as your final regression output. So what do you do in such case, right? This is your final. So your question now is, how do you find this value g, this function g, which you're able to sort of correct the outputs given by your friend's model? So what do you do? How would you find? How would you create g? What would be the criteria you're going to use for creating g? So if you look at the example over here, this is what we want. In the ideal case, we want g of x1 to be exactly y1 minus f of x1, right? You want exactly the error in your friend's model to be predicted correctly by g, and then your g of x plus f of x will give you the correct answer. So that's exactly what you have to do. You have to train a model using the input x1, x2, x3, etc., and the outputs as y minus f of x1, what's called the residual. So you have to train a model, a simple regression model, on the residual of the model before it, right? And this gives you a better model. When you do f of x, when you do f of x plus g of x as your final output, that is actually going to be better than just having f of x. And the great thing about this is that you can create a model on top of this, right? You can create not just g, but you can create g1, g2, g3, which is taking the outputs of the models so far, and it's the residuals of that it's taking, and it is learning to predict that. It's learning to predict basically how to course correct the model outputs for any given input. So this is the idea behind gradient boosting. You continuously keep on doing this, and you keep on training models on the residuals. This is really the essential idea. It's not much more complicated than this, but requires a little bit of thought into why this actually works. So now let's discuss how this works, and why it's related to gradient descent, and why the gradient part comes in this boosting procedure. So like we said, we had the loss function, which is just over here, the squared loss, right? You're dividing it by 2, and this is a very okay thing to do. You can always scale your losses by any value. It won't change the model you're obtaining. So now we want to minimize this, and we want to do this by adjusting f of x1, x2, and xn, right? Now these are just some numbers. These values, these outputs of the model f is just some numbers. So you can treat them as parameters, and you can basically calculate the derivative with respect to this derivative of this loss. The loss over here is your simple loss function, your squared loss, right? So what is the derivative of j, which is your total squared loss, with respect to each of your data points, right? Each of the outputs of your function f, rather the predictions of your function f. If you calculate that and you work it out over here, it turns out it's actually the residual. So the gradient over here is actually just your residual, right? Just your prediction minus your true value y1. And this is a very interesting property, because this means that as you're adding more models, you're actually doing a sort of gradient descent in the space of the predicted values f of x1, right? And so you can interpret these, you can use each of these as being a negative gradient. And so what happens is that instead of having your predictions, instead of having weights as you normally do with linear regression, you have a vector of your residuals, right? Which is your predicted y1 y minus f of x1. That vector becomes your sort of weights. And so with gradient descent, as you add one more model, that is basically equivalent to taking a step, you change your residuals which you're obtaining from the combined model f of x1 plus g of x1, f of x plus g1 of x plus g2 of x plus g3 of x. As you add more and more models that way, you are essentially changing the residuals, and you are doing gradient descent to update the residuals as if they were weights. And the reason for this is because for squared loss, the derivative is actually just a residual. The gradient is just a residual. So as you see over here, very similar to how you have your thetas, your weights, you're basically just doing a gradient descent on the residuals itself, right? So this is a very interesting way in which boosting using this simple rule is actually related to gradient descent. And this is, there's something called functional gradient descent, which is basically what is happening over here. You can go and look up functional gradient descent to really understand some of the mathematical concepts. But gradient boosting is a very powerful procedure. It's used a lot in very popular tools like LightGBM and XGBoost. So it is something that is very practical as well, in addition to AdaBoost. And so, in general, this is the overall procedure. As you see, you initialize it, just by using some. You can initialize the initial model to be whatever. This is, remember, the model given to you by your friend. So it doesn't have to be a very good model. You can just use, for example, for every input x, it just predicts the mean value of all the targets. If you just take the average value, it'll just predict that. So it's just a simple heuristic rule also will work. And then iteratively, you are computing this residual RIM for each of the I examples. M is the number of rounds over here. So for each of those, you're calculating the residual value of the gradient. The residual value is the gradient, sorry. And you're fitting a regression tree such that you are actually predicting the residuals. You're trying to predict the y minus f of x. You're trying to predict that value. You're trying to predict basically the error made by the model so far, right? That is what you're trying to predict. And then you, of course, add them together. Sorry. You add them together to get your final model. And you iteratively do this, so you create f of f0 of x plus f1 of x plus f2 of x, so on and so forth, up to fmx. So you'll create this sum of f of m models to be your final model, right? And then you use that as your regression output. And so the idea is basically that the first model is sort of wrong, the second model is trained on the errors of that, the third model is trained on the errors of the first two models combined, the fourth model is trained on the errors of the first three models combined, so on and so forth. So you are slowly narrowing and reducing the total error which is made by the total combined model. And this gives you a final model which is very low bias, and also it's a very good predictor. This works for regression. For classification, you have to do a few modifications to this algorithm to get it to work. So finally, just to sum up on gradient boosting, it's boosting plus gradient descent. It's boosting because you're iteratively trying to reduce the errors of the models previous, and you're creating new and new models as you're doing it. And the real key of boosting is that each model itself does not need to be a very powerful learner. It doesn't need to be something like a neural network. It can be a very simple decision tree, or even a decision tree with just one rule, which is called a decision stump. And over a number of rounds, you're iteratively using that simple learning algorithm to create a better and better classifier, or a better and better regression model, right? So in each round, you introduce a weak learner to compensate for the shortcomings of the existing weak learners. Now, the difference between AdaBoost and gradient boosting is that in AdaBoost, the shortcomings are identified by your high weighted data points. The vector where the probability scores were high, that is how you identified which data points to focus on. Over here, the data points are identified by the gradients, the residuals, essentially. And where there's a very high residual value, that means the model so far is not able to predict it very well, and therefore the model should learn that much better. So both high weighted data points and gradients, they tell us how to improve our final combined model in the boosting procedure. Okay, that should be it from my side. Thank you so much for listening to me, and I hope you enjoy the rest of the series.
Hello everyone. My name is Mayank Sharma and I'm an applied scientist at Amazon Prime Video International Expansion team. Welcome to the third lecture in the Supervised Learning module. So today I shall be discussing some of the evaluation metrics and supplementary topics in Supervised Learning. The order of the presentation will be as follows. We'll discuss some of the evaluation metrics which are typically used for classification and regression tasks. We'll talk about how multi-class classification is performed. We'll talk about some of the classifiers which are typically used, such as naive Bayes classifier, k-nearest neighbor classifier, support vector machine classifier. And then we'll finally talk about how do you perform model selection. So let's begin with evaluation metric. Now, evaluation metrics explain the performance of a model. Evaluating a model is core part of building an effective machine learning model pipeline. What happens is that generally you build a model, you get feedback from the metrics which you compute about the model. You make improvements to the model based on those metrics, and then you continue that process until you achieve a desired level of, let's say, accuracy. Now, the choice of the metric completely depends on the type of model and the problem at hand which you're working on. So we shall cover the following classification and regression metrics as shown on this slide. Now, let's look at a problem of predicting if a customer transaction is fraudulent or not. So on the figure, what you see is the order stream, right? The blue ones or the blue points are the good orders, and the red one are fraudulent orders. Now, what you would do naively, you would manually look at each of these points or each of these orders, assess the attributes or the features of these orders, and decide whether this order is fraudulent or not. However, this is not scalable process, right? With millions of transactions happening, let's say on Amazon, doing it manually is very difficult. So what do? You automate the process by building a machine learning model. What that machine learning model does, it scores these transactions based on some of the features of these transactions. And then it provides a risk score, right? Higher the risk score, the more chances it is for that transaction to be fraudulent. Lower the risk score, lower are the chances for that transaction to be non-fraudulent, or it's a good transaction. So using this machine learning model, you get a good separation of the data. However, please note that the separation can never be perfect, because it might so happen that some of the fraudulent transaction would look like a good transaction and vice versa. Okay. Now, as I said, the machine learning model will provide you a risk score. Higher it's bad, lower it's good. Now, typically these scores are probabilistic, as you have already studied in the previous lectures, right? So you get a probability that an order, it's a fraud or it's a good transaction, right? And then you rank them, right, based on the order of the score. So this is the kind of segregation you get. If your model is good, you get a good separation of good and bad score. Otherwise, you don't get a good separation, right? So right now we can say that, hey, our model is pretty decent because the red or the fraudulent are on one side, and blue or non-fraudulent are on the other side. And as I said, the model is never perfect, so there may be some mix and match here and there. Okay. So where would you draw a line, right, which would separate these two classes, right, or these two categories, fraudulent and non-fraudulent? Where would you draw a line, right? I would typically draw somewhere here, right? Okay. So typically what we do in a machine learning model, once you train it, we select some probability threshold. Let's say we select a threshold of 0.5 and say that all the transactions with score greater than 0.5 are fraudulent, and all the transactions with scores or probability less than 0.5 are non-fraudulent. As I said, separation may or may not be perfect. Okay. So what happens is, once you tag something as fraudulent, this goes to humans to verify whether this is actually a fraudulent transaction or not. Okay, While doing so, what might so happen is there might be these non-fraudulent transactions which would also go to human, and then it might take some time for human to verify. You might delay some order, but it's better than uh, allowing these fraudulent transactions to pass by. Okay. Now, what happens if you change the threshold, right? Let's say you change the, initially it was 0.5, now it's, let's say, 0.3, right? So what would happen here in this case is more and more transaction on the right side of this threshold would be marked as fraud, and more of them would go to humans, right? So the effort of humans in checking of these transactions would increase, right? Because more transactions are going to humans now, and will delay the orders. What would happen if you, let's say, select a threshold of 0.8 or 0.9, which is something like this, more towards the right side? What would happen in that case is lesser number of fraudulent transaction would go to humans, and more fraudulent transaction would pass through, right? And this would cost dearly for the company. You don't want that these fraudulent transaction to pass by, right? So it's pretty important to select the right threshold, which actually separates out the data in the best way, right? And how do you select this threshold is based again on the problem at hand and the metrics which you choose for that problem. So we'll now move towards explaining these metrics or these choices of metrics, right? So the first thing we'll talk about is a confusion matrix. A confusion matrix is an n by n matrix where n is the number of classes which are being predicted. Uh, Typically, it's basically a performance measurement for a classification algorithm where, as I said, it can be binary or a multi-class classification. So typically for a binary classification, on the left-hand side, you'll see an example, pictorial example. For, let's say, for each of the sample, you might have a true label, which is either 1 or a 0. So this is the true label. Similarly, based on the thresholding, the model would either predict 1 or a 0 for that given data point, right? So let's take this example. So there can be 4 possible cases, right? When the actual value is 1 and your predicted value is 1, it's known as true positive. So this example specifies this. So let's say a pregnant woman goes to a gynecologist, and gynecologist, after assessing the condition, says that the woman is pregnant. This is a true positive case. Let's talk about true negative case. If a male goes to a gynecologist and then the gynecologist says that you're not pregnant because it's unlikely for a male to get pregnant, and hence this is a true negative, right? Because the actual value is also 0, predicted value is also 0. What happens, let's say a male goes to a gynecologist and he says that, hey, you're pregnant. This is typically not possible, and hence this is false positive, because the model, which is the gynecologist, it's saying the male is pregnant, which is positive case, and it is wrong, and hence it is false positive. Similarly, you have false negative case, right? A woman goes to a gynecologist, she is actually pregnant, the true value is 1, however the gynecologist says you are not pregnant, so this is false negative case, right? On the right hand side, this is a concise representation of the same figure. TP represent true positive, FP represent false positive, FN represent false negative, and TN represent false negatives. Okay, now consider the figure on the right hand side, right? So just consider this square for now, and this center line, right? Anything to the left of the center line is a positive example. True positive, the actual labels of these are 1. Anything on the right hand side, which is the light gray region, and this pink region, is basically uh, uh, all the examples with true label as 0, right? Let's consider 1 and 0 for now. Now consider a machine learning classification model with some threshold, right? So anything, this is what a machine learning model predicts. Anything inside this circle, the model predicts as 1. It may or may not be right, as you can see from the figure. Anything which is outside this circle, the model predicts as 0, right? Again, the model may or may not be perfectly correct. Okay. Okay, so anything which is inside this green semicircle indicates true positive. That is, the whatever the model has predicted as 1, and they are all the true. The actual label is also 1. The pink classes are the false positive cases. That is, model has predicted them to be 1. However, their actual label is 0, and hence these are false positive. Anything in this region to the left of the semicircle and the dark gray region is false negative because their actual label was 1. However, the model has predicted it to be 0. Anything on the right and outside this peach or the pink color are the true negative because model has predicted them to be negative and their true label was also negative or 0. Okay, so we'll compute the following metrics such as precision, recall, false positive rate, true negative rate, and so on and so forth. So let's talk about what is precision, right? Precision is basically what it says is how correct you are on the ones you have predicted as positive, right? So take this example, pictorially example, this would be really helpful in understanding. So precision is basically this green semicircle to this complete circle, right? Which it says that how many actual positive it predicted to the total positives it predicted, right? So this is precision. Similarly, you can compute the recall. Again, look for this figure for recall here, which says that what fraction of positives did you correctly predict, right? So the model might not predict all the positives, all the actual positive as positive. It might only predict a fraction of them as positive, and that fraction is known as recall. It is also known as sensitivity or true positive rate, right? As the name suggests, true positive rate means the true positives from the model to the total positive, right? And hence the name true positivity rate. Similarly, you can also compute false positivity rate. As the name suggests, what the false positive rate is the fraction of negative samples which you uh, correctly predicted, which you wrongly predicted, right? Okay, so these are the false positive which the model predicted, right? So this each segment, and the total negatives were this, right? These were the actual negative. So it's basically the ratio that how many false positive you selected out of the total negative samples. So this is the false positive rate. Similarly, you can also compute true negativity rate. The true negativity rate is basically the fraction of actual negative samples which you correctly predicted, right? So from this figure, this is the sample set which the model said, hey, I am confident that these are negative to the total negative. So this is the true negativity rate, or it is known as specificity. Okay. There are also two different other matrices which you typically compute for a given classification model, right? Let's say your data set is balanced, right, with equal number of samples in each class. So what you do is you also compute the accuracy of the model, right? The accuracy is denoted as the ratio of total correct prediction to the total number of samples, right? So the total correct predictions were this green block and this part of the square where the model has predicted the true negatives. So it's basically the sum of true positive plus true negative divided by the total number of samples, right? However, for imbalanced data set wherein the number of samples of one class is pretty higher than the number of sample of the other class, the accuracy metric is misleading. Now let's take an example. Consider that your data set contains 95 negative samples and 5 positive samples, right? And your model predicts everything as negative, right? So if you compute the accuracy in this case, it would be 95% accuracy or 0.95. I have not multiplied by 100. Okay. You can also multiply it by 100 to get 95% accuracy. So is this the right metric you should look for? No, because you're not taking into account these 5 positive classes or these rare classes, right? And hence the accuracy is not the right metric. So what you do in this case is you compute the balanced accuracy measure. What it does is that it normalizes the true positive and the true negative prediction by the total number of positive and negative samples. So you are taking into account the amount of positive and the negative samples, right? So what you do is you take the true positive samples, you divide it by the total number of positive samples. You take the true negative samples, you divide it by the total number of negative samples, and you take the average of the two, right? So if for the above example of 95 negative and 5 positive values, For the first negative class, you get a balanced you get the true positivity rate of 1. For the other class, since you are not predicting anything, you get a true negativity rate of 0. You take the average and you get a value of 0.5. This is a better measure than accuracy, right? You're saying, hey, my model is 95% accurate, but you're not selecting anything about the other class. However, this takes into account the imbalance, and hence this is a better measure. Okay, now let's take an example to understand more, right? Let the true labels for a given 7 samples be this, right? 0, 1, 0, 1, so on and so forth. You have the predicted scores, which are probabilistic, right? For a given classifier, 0.5, 0.9, 0.7, 0.7, so on and so forth. Then what do you do? As I said, you select a threshold and you say above this threshold, the predicted label is 1. Below this threshold, the predicted label is 0. Let's select the threshold of 0.6. So for this sample, the label predicted label would be 0. For this, the predicted label would be 1, 1, 1, 0, 0, 0. Okay. Now let's compute accuracy, recall, and precision. So let's first compute accuracy, right? Now, what is accuracy? As I said, total number of correct predictions to the total number of samples, right? So in this case, the total number of correct predictions are basically 4, right? So here, 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 and here. The model has predicted 0 and the actual label is 0. Model has predicted 1. This is also 1, and so on and so forth. So the accuracy is 4 divided by total number of samples, which is 4 by 7. Now let's compute recall, right? What does recall say? Recall says that what is it true positive to the total number of positive cases, right? The true positive cases are only these 2, right? And the total positive cases are these 4, right? Total actual positive cases. So the recall would be 2 by 4, which is 1 by 2. Let's compute precision, right? Precision is the ratio of true positive to true positive plus false positive, right? So true positive to the total number of positive which are predicted by the model, not the actual values. So total true positive are 2, and this is 1 false positive, right? Because the model has predicted 1 and the actual number is 0, right? So in this case, the precision would be 2 by 3. These 2 divided by total number of true values which are predicted by the model, true positive plus false positive cases. Okay. Now, when deploying a model in real life, as I said, you have to take into account various metrics, various thresholds, right? So a good practice is to plot a precision recall curve, right? And as I said, how do you decide the threshold? The threshold depends on the problem at hand. So let's take an example. So on the right hand side, you'll see a precision recall curve. On the y-axis, you have precision. On the x-axis, you have recall. And this plot is basically you select different thresholds, right? And for that threshold, you compute recall. Let's say compute precision and recall for threshold of 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, and 0, right? And you get a curve. So let's take the first example, right? Where let's take an example of movie recommendation in Prime Video, right? Okay. So you open a Prime Video page, you select that, hey, show me a movie based on, let's say, some genre X, right? The genre can be action, comedy, drama, and so on and so forth. Now, if you're, what you would ideally like, right? We would ideally like to recommend the correct genres of movies, right? Even though we may miss out on several movies of that same genre, right? You would want to show that, hey, these are the possible some subset of collection of the movies which belong to the same genre. You may or may not want to show all the movies in that genre to the user, right? So what does this mean is that you want high true positivity rate, right? Which implies you don't want to show movies of wrong genre, right? If you have selected comedy, right, you don't want to show an action movie to the user, right? And hence, which implies you need high precision here, right? So you plot the precision recall curve at various threshold, and then you choose a threshold such that the precision is high, but you may be okay with low recall. Okay, so this is the first case. Now, consider a rare event detection case, right? Such as, let's say, a cancer detection or a COVID detection, right? Now, You would ideally want that if a person has a disease, it should be caught during the test, right? You don't want that it should not be caught during the test, and that would have disaster consequences, right? So, which implies you're going with high recall value, right? So, which it says that whenever it exists, you should catch it, right? Which implies high recall, right? We may be okay with lower precision in this case, right? Because you can, if the even if you flag somebody as having cancer, you can go for another round of test, and then it would be um, nullified there, even if the person don't have a cancer. Okay. Now, there's another metric known as receiver operating characteristic curve, or ROC curve. And then I'll also talk about AUC. Now, the ROC curve is a graphical plot, right, as shown here, that illustrates the diagnostic ability of a binary classifier system uh, as you vary the threshold for that system, right? So, how this ROC curve is created? On the x-axis, you have a false positivity rate. On the y-axis, you have the true positivity rate. Okay. And then let's take an example of a model as shown in blue, right? You again, same thing you do in precision recall curve. You select a threshold, you compute precision recall. Here you'll compute true positivity rate and false positivity rate, right? Let's say at a threshold of 0.1, this is the value. At 0.2, this is the value. 0.6, this is the value. 0.7, this is the value. 0.8, this is the value. 0.9, this is the value, and so on and so forth, right? So as the threshold is varied, you compute true positivity rate and false positivity rate, and you plot it, right? Now, the best classifier ideally would be, you want a zero false positivity rate and a very high true positivity rate. So 0, 1 in this plot would be the perfect classifier. But generally this does not happen because of the variability in the data itself, right? The diagonal line divides the plane into two parts, right? This diagonal line is associated with a random classifier. Random means you toss a coin and then randomly provide the output for a given problem, right? So you'll get this line. Okay. Anything which is above this random classifier is good. And how let's consider these three models, right? So as I said, going this way is better, going this way is worse, because by going this way, you're going towards the perfect classifier, which has zero false positive rate, that is, does not make mistake and always predict something which is true, right? So you ideally would want to push this way. Now, out of these three, which one would be the best classifier, right? Let's say you have three different type of classifier, and these are the ROC curve for these three classifiers. So which would be the best? The blue one would be the best because it is more closer to the perfect classifier value. Now, a bit of trivia about the name ROC, right? We talk about ROC and all, receiver operator characteristic. What does this name mean? So the ROC curve was first used during the World War II, and it was used for the analysis of radar signal. Now, why it was used? Following the attack on Pearl Harbor in 1941 by Japanese army, the US army wanted to know the prediction, how good the prediction is to detect the Japanese aircraft from their radar signal. And for this purpose, they measured the ability of the radar receiver operator to make these distinction, and hence the name receiver operating characteristic. It comes from radar receiver operating radar receiver operator. Okay. We can also compute the area under this curve, right? So as I said, the more you go here, the area under this curve, which is denoted by this, right? Which is denoted by this, increases. This area increases as you move towards this direction, right? So you can also compute the area under the curve, right? The more the area, the better the classifier, right? It can be understood as the probability that the model ranks a random positive example more highly than a random negative example, right? The perfect AUC is one, which would be here. This would be the perfect classifier. the random AUC is 0.5, which would be the area under this random classifier curve. You can compute the area is half into base into height. Half base is 1, height is 1, so and hence the random AUC is 0.5. The advantage of AUC is that it's scale invariant and classifier threshold invariant, right? Because you compute the AUC across all the thresholds. So consider the problem of classifying a mail as spam versus no spam, right? Assume that the emails are ranked by the classifier risk score, right? On the left is high scoring mails, which should be classified as a spam mail, and on the right are the low risk or low probability mails, which should be classified as no spam, right? And here is the ROC curve, which is again the plot of true positivity rate to false positivity rate, right? You plot the ROC curve as mentioned before by plotting the TPR and FPR at various threshold, right? Now, how do you select the best threshold, right? Or the best threshold below which you would mark as below which you'll mark as spam, and below which you'll mark as non-spam, and above which you mark as spam, right? So what you do is you look at this ROC curve. You typically look for the knee point, right? And that knee point is basically saying that, hey, at this knee point, your false positivity rate is low, but your true positivity rate is high, which implies you would mark the true spam as spam, and you'll mark the true non-spam as non-spam. There might be 10 to 15% for false flagging, which is okay for me, depending on my problem, right? So this is known as the operational point. It is the point at which the TPR minus FPR is maximum. Okay. Now, after talking about all these metrics, we'll talk about multi-class classification, right? Till now, we have only discussed binary classification. However, in the real world, the data is multi-class. So let's take an example of an image classification task. Let's say you have to classify this image to the model. Now, this image could be of a dog, it could be of a cat, it could be of a bus, car, human, traffic signal, and so on and so forth. There can be multiple categories. For ImageNet dataset, you have close to 1,000 categories, and for other, you have even 10,000 categories, right? So for such cases, we need to expand our capability of a binary classification to a multi-class setting, right? So there are two generally used scenarios for multi-class classification. Number one is one versus the rest, right? So in this case, let's consider this figure. There are three different samples of three different classes. One is of a triangle, one is of a square, one is of a cross, right? So what does your intuition say? You convert this into binary classification problem, three binary classification problem. The number one problem would be considering this as positive example, triangle as positive, and the remaining two as negative sample. You have one binary classification problem. You have another binary classification problem by considering these squares as positive and these as negative class, right? And you have a third binary classification problem by considering this as a positive class and these two as negative class, right? Then you train three different models, right? You'll get three different lines. If you get during test time, once you get a sample, you pass the sample through all the three model and select the model, select the class for which the value is most positive, right? So let's say a sample during test time comes here. You compute the prediction value for this model, it comes out to be negative. For this model, it comes out to be positive, and for this model, it comes out to be negative. And hence you'll say, hey, my new sample belongs to class number this, the square class, right? Similarly, or we can use a softmax based classifier, which is another way of converting, another way of multi-class classification, right? Now, recall that in your previous modules, you might have studied about logistic function that computes the value between 1 and 0 and 1, right? For example, a logistic regression output of 0.8 from an email classifier suggests that there is an 80% chance of that email to be spam and 20% chance that it is not a spam or a good mail, right? And the sum of the probabilities is 1, right? So in a multi-class softmax classifier, what you do is you for all the possible classes, let's say there are k classes, capital K classes. For each of the classes, you get a probability, and these probabilities sum to 1, right? And this probability for a given sample to be of the class K, small k, right? Let's say this is the image of a dog, and the probability that it belongs to a dog is given by e to the power wk xi, where xi are the features, wk is the weight vector associated with that class, and you normalize it across all the different classes, right? Let's take this example. Let's pass this to a softmax classifier. The softmax classifier will give you probabilities that it belongs to dog with probability 0.8, muffin with 0.1, cat with 0.05, and bird with 0.05, right? So there's w k means you'll have a wk for w for dog, you'll have a w, different w for muffin, different w for cat, and different w for bird. Okay. Till now, we have talked about classification metrics. Let's talk in brief about regression metrics as well. Consider n blue data points. These are your data points, right? Fx be the line that fits the data. It might so happen the best line may not pass through any data point. Now, consider this data point. The error is determined by yi minus f of xi. So this distance is the error, right? Using this error, you can compute root mean square error, which is the square of this error divided by the total number of samples across summed across all the samples, and you take a square root of it. Similarly, you can compute mean absolute percentage error, and you can also compute R square. R square is basically the coefficient of determination. It provides a measure of how well observed outcomes are replicated by the model, or more simply, it evaluates the scatter of the data around the fitted regression line, right? It is based on the proportion of total variation of outcomes, which is these error explained by the model, right? It's basically a statistical measure of how well the regression predicts the real data point, right? How well this line predicts these, right? So the formula is given by this. So y minus f of xi is basically the square of the error. Y minus y bar is the variance of the label data, how this data is varying across the mean of these labels. And R square is basically 1 minus residual sum of square and the variance of the label data. Okay. Now we'll move to some supplementary topics such as naive Bayes, k-nearest classifier, and so on and so forth. Okay. Now, the naive Bayes classifier is basically a classification technique which is based on Bayes theorem, right? And with the assumption that there is an independence among the feature. So if I talk in more simpler terms, a naive Bayes classifier assumes that the presence of a particular feature in a class is unrelated to presence of any other feature, right? So that means the features are independent given the class. Let's take an example. Let's consider a fruit, right? A fruit may, let's say the fruit is apple. Now that fruit will be considered as an apple if it is red, it is round, and it's about, let's say, 3 to 4 inches in diameter, right? Now, even though these features, without knowing that this is an apple, these features might be related, right? But if you know these features, if you know that it is an apple, right? So these features become independent of each other, right? So this is the naive assumption which you're making, right? In real world, these features may be related, but the assumption which you're making is given you know the class or the category of the data, these features would be independent of each other. So this is what it says. The class probability, the model computes the probability that this point xi has the class yi, which can be computed using the Bayes theorem as p of yi into p of xi given yi. P of yi you can compute from the data, and this p of xi given yi, now xi is an apple. An apple consists of, let's say, 3 features, right? As I said, red, round, and the diameter, right? So the Bayes theorem says that the features in xi are independent of each other given yi, and hence you can write it as the product of probabilities, right? So in naive Bayes classifier, there is no training as such, right? So there is a learning which simply involves computing the class conditional probabilities from the training data itself. You have to compute this value from the training data, right? Now the advantage is that the learning is straightforward. It's really fast during learning as well as prediction time, because there's no training involved, right? Just you need to compute these tables from the training data, right? So if you have 10 features and 2 classes, it will be a 10 cross 2 matrix. You need to just compute this 10 cross 2 matrix from the data itself. Now, as I said, there are cons to this as well, because it's naive. So the class conditional independence might not always hold. The smoothing might be required for sparse features, right? Now let's move to k-nearest neighbor classifier, right? The k-nearest neighbor assume that similar thing exists in close proximity with each other, right? So let's take this example. There are 2 classes. The samples of class 1 are close to each other, and sample of class 2 are close to each other, but the samples of which are not, which are of different classes are far apart. So this and these are far apart, whereas this and this are close. Okay, so how do you compute when a new point comes, right? Let's say this cross is the new point during test time. What you do is you look in some local neighborhood of that point. Let's say you find that in this local neighborhood there are 6 or 7 points, and all the labels of those 6 and 7 points are blue, and hence this new point would be labeled as blue, right? It can also be used for regression. So instead of classifying this point, you compute the average of this point, and this would be the regression value for this new point. The nearest neighbor may be calculated using KD tree and locality semantic hashing. Okay. Now there is an effect of the neighborhood size, right? This neighborhood size can be this big, it can be this big, it can be this big, right? And hence uh, the boundary, or the separating boundary which you get from the k-nearest classifier varies, right? If the k is very small, you get jagged boundaries, very jagged boundaries. You can see pockets and all. So it is a nonlinear classifier, but if the k is very small, the boundaries you get is very jagged. However, if you take a huge neighborhood, so you sort of average out the variations, right? And hence you get a smoother boundary between the two classes. Okay. However, k-nearest neighbor suffers from the phenomenon known as curse of dimensionality. Now, um, what it says is, as we move to higher and higher dimension, the data fills less and less space of that dimension, right? And hence, in order to maintain an accurate representation of that problem, you need more and more samples. So the number of samples have to grow exponentially. So this is the curse of dimensionality, right? So let's take this example, right? Um, so if you're able to see the screen properly, let's say you sample 10 to 15 points or 20 points uniformly in the range 0 to 20 in one dimension, right? And consider these 5 regions of length uh, uh, 5, these 4 regions of length 5 each, right? So to have these 20 samples, you just need 4 regions. You have 4 regions, right? Uh, but if you move to 2D and you randomly sample from 20, uniformly randomly sample from 20 cross 20 grid, and let's say 15 to 20 samples, you see there are 16 regions, right? And a majority of the regions are empty, right? Similarly, if you go to 3 dimension, you'll have 64 regions, right, for 20 samples. So a majority of those 64 blocks would be empty, right? This is what this right figure is trying to say, that as you go to higher and higher dimension, the number of samples in each of those cubic region, right, which is in this example 5 cross 5 cross 5 for 3 dimension decreases, right? Okay. There is another problem associated with curse of dimensionality, right? Let's consider a fixed number of random points are generated from a uniform distribution in D dimension, where D can be 1, 2, 4, and up to 128, right? What we do is we compute the pairwise distances across all these random points. Let's say we have k random points, you compute k square distances. and then you normalize them by the maximum distance. What you do here is then you plot, right, the frequency of the distances, right? Since the distances are normalized, so the value will lie between 0 and 1. And on the x-axis, you compute the frequency of those distances, right? What's the number of samples which go in the range between 0 to 2? It's close to 1, so on and so forth. So most of the there are multiple samples in the range 0 to 2, 0.2 to 4, and 0.8 to 1. Now, but as the number of dimension increases, right, we see that the spread decreases, right, as the number of dimension increases, right, which implies that more and more samples have similar distances, have same distances, right? Let's say here in 128 dimension, this is peaked at 0.6. So what you can conclude is more and more samples have a distance of 0.6. Any pair you choose, and that pair would have a distance of 0.6. Now, as explained before, k nearest neighbor works on the distances, right, on the neighborhood. Now, if all the distances are approximately equal to 0.6, right, k nearest neighbor would fail, right, and hence it is good to work in for k nearest neighbor to work in low dimension spaces. We can also talk about support vector machine kind of classifier, right? So let's take an example, right? So this is the samples of positive class. This is the sample of negative class, right? You have 3 different options to choose, right? This is the red line, green line, and blue line. What do you think is the best line, right? The blue line is a decent classifier because it separates the two. The green line is also a decent classifier because it separates the two. However, if you consider this gray test point, right, the blue line will make a wrong decision, right? But just on visual inspection, you'll see that this belongs to the positive class, right? So the green one actually classifies them the best. Right? Now, the interesting feature which I've not mentioned is the gray dotted line, right? These lines represent no man's land in which no observation should fall, right? So this each strip of these gray line can be viewed as a margin of error, right? Because no sample should fall here. Now these two margins are computed as the parallel lines that maximizes the distance between the samples of the two class. So this is the distance between the samples of two class, and these lines are plotted such that the distance between the samples of two classes is maximized, right? These line passes through some of the samples of class 1 and some of the samples of class 2, and these samples through which the line passes are known as support vector, right? So now you haven't answered the question why green line is better, because the margin or the separation between the two classes is maximum for the green line, right? The core idea of the SVM is to maximize the margin under the constraint that the classifier does not make any mistake, right? Okay. So the SVM solved the following optimization problem when the data is linearly separable, right? You would want that all the samples of class 1 are on the right hand side of the this margin. All the samples of class -1 are on the left hand side of this this gray line, right? Which is equivalent to saying y w transpose xi plus b is greater than 1, and the margin is denoted by 1 by norm of w square. So what you would want is to maximize the margin, right? To maximize this inverse function is equivalent to minimizing the opposite of this, which is minimizing half norm w square under the constraint that the samples of class 1 should be above this, the samples of class -1 should be below this, right? And hence you get w transpose xi plus b equal to 0 once you solve this problem as the model, SVM model. However, there are cases when the data set is not linearly separable. In such cases, to obtain a linear classifier, barring few errors, you use a slack variable. Let's take this example, right? So these 2 points make the data set not linearly separable. However, you can make them linearly separable by pushing these here and pushing these here. And this is what slack variable does. It pushes these points out of this margin area, right? And hence you get an optimization problem of this sort. Not going into detail here, There is another case, right? Till now, we have only talked about linear classifier, right? Even after adding slack variables, you'll still get a linear classifier, but there are cases when this might not hold. And in fact, in most of the cases, this does not hold, right? Consider this case, right? You have two concentric circle, one here of class one here of class -1. There is no line you can make which would separate the two. However, you can do something clever, right? You can transform this data into polar coordinate, right, by x square plus y square. In this polar coordinate, this data set is separable, as you can see here. And then you can draw a line, right? You can use an SVM in this space, right? And if you turn it back to the original space, this line corresponds to this circle, right? So this is known as transformation using a function or a kernel, right? You transform xi into some z of xi, this z space in which the data set is linearly separable, and you perform an SVM. Typically, SVMs are solved in dual form of the optimization. What I showed you initially was the primal. You can convert into a dual format. The advantage of the dual format is it allows for creating a non-linear mapping Z without explicitly computing this Z, right? You can, because in this dual form, you have the dot product of this mapping, and this dot product can be some function which you choose, right, based on some properties of the function, right? This can be a radial basis functions shown here. It can be a polynomial function. It can be a tangent kernel, right? So this is an example. Consider this 2 moons data set, right? This is not a linearly separable data set, as you can see. If you use nearest neighbor with some neighborhood value of k, you would get this kind of a classifier, and you get close to 97% accuracy. If you choose a linear SVM, you only get 88% accuracy. However, if you choose a RBF SVM, that means you're using this function, right? That means you're mapping it to some higher dimension using this function. You get this kind of classifier and you get 97% accuracy. Okay. Lastly, we'll talk about model selection. Till now, we have only discussed evaluation metrics and some classifiers. Now, right? For a given problem, you typically have to train several models and then select the best model. Now, for each model, you also have several knobs to tune, right? Now, we'll now talk about how to select these best model type out of all the models which you have trained for a problem across various settings of these knobs, right? And this is known as model selection. Now, typically, you for a given problem, you train several different models and select. You want to select based on some metric, right? And here we provide a paradigm for proper model selection, right? Uh, Typically, you get your data is shown here, all the data. What generally people do is you train on this data only and test on this data. This is incorrect. Ideally, what you should do is you should keep a part of training data separate, call it as training data, keep the part of all data separate from the training data and call it test data, right? And then you should train here and then test your model here. Typically, different classifier, as I said, have different hyperparameter or knobs you can tune, right? Let's say for linear model, you have regularization coefficient. For SVM, you have C, gamma, and other coefficient. For random forest, you have number of trees, depth, leaf size, and so on and so forth, right? So let's say we have decided on a metric, right? That metric is accuracy, right? And then what you want to do is select the best possible value of the knob or the hyperparameter for that decision tree, for which you get the optimal performance on the test set. So what do you do is you consider the train and test set of the data. You consider, let's say you have, for example, you consider only the depth of the tree, right? You build a decision tree with the maximum depth, compute the train and test accuracy, then you choose this depth 1, depth 2, depth 3, depth 4, so on and so forth. You compute the train and test accuracy, right? So you'll get a plot something like this, right? For a single test train partition, right? For one depth, the accuracy is 0.6. For 4 depth, it's 0.9, and so on and so forth, right? And after this, the accuracy does not change much. So ideally, you would select this model as your best model because train and test curve follow the same similar curves, and the best accuracy on the test you get here at 4. However, when evaluating the hyperparameter, there's still a risk of overfitting on the test set, right? Because the parameters you have tubed are on the test set only, right? Now, this way, the knowledge about the test set can leak into the model, right? And model might not perform well on new unseen data apart from the test set. So you have taken one test set, perform everything there, right? You selected the best parameter. However, when you go to the real world exam, real life data, the model would fail because it has only it has been tweaked the best for the test set only, right? To solve this problem, so what we do is we create yet another partition of the training data known as validation set, right? Initially, you had all the data, you perform two partition, now you perform three partition, right? Yellow, green, and blue. Okay. Now, a test set is still held out for the final evaluation, right? The issue with this kind of approach is since you are dividing into three parts, the number of training samples would reduce drastically, right? And hence, when you perform the hyperparameter tuning on this validation data and perform on test data, the performance might not be as good, right? So what you do in this case is you do a k-fold cross validation. What you do is you take this training data, divide into, let's say, 5 segments. You can divide into more or less depending on the problem statement. Typically, people divide it into 5 segments. You consider one of the fold as the validation fold and the remaining as training fold, right? You combine these four, train on this, tune the hyperparameter on this. In the next step, you train on 1, 3, 4, 5, validate on 2, and so on and so forth. And then you take the average out of these, right? And based on this average value, select the best hyperparameter. And then finally, once you are happy with the hyperparameter setting, you take that hyperparameter setting, train the model on this data for that given hyperparameter setting and test on this data. Okay. Now, there are multiple ways to do hyperparameter tuning. One is grid search, one is random search, right? Grid search, you take all the parameters, keep them in nested for loop, and then perform k-fold cross validation on each, determine the average error, and then select the best parameter based on the average error. There is also another type of parameter search which is known as random search, right? For you fix a number of iteration, you select these hyperparameter, each of the hyperparameter randomly from a certain range. You perform a k-fold cross validation and determine the average. In this case, there is no guarantee that you would find the best parameter because you're not going through all the parameter. You're only going through some number of iterations. However, this is typically faster and you can do a parallel search here. Lastly, I'd like to leave you with some of the modeling tips for training and testing of the model, right? Typically, as we see in machine learning and with the emerging deep learning technologies, more training examples, the better, right? Because the larger training set leads to better generalization on unseen examples. The more feature is typically better, right? Typically people invest time in feature engineering to construct the optimal set of feature for a given signal. As I said, people typically make mistake by evaluating the performance on the same data as which was used for training, which is wrong, right? And then you should perform k-fold cross validation if your model permits that. You should pay attention to training data quality. This is the most important part here. Typically, you would find data from which are open source from universities and all. They are typically of good quality. However, if you get data from non-open source, or you get data which is coming from transaction data and all, the data might not be very good, right? So you need to remove outliers, you need to remove target leakers, you need to remove garbage data and so on and so forth. So that is the most important. If your data quality is bad, the model trained would be bad, right? So this is the most important thing to take into account. And as I said, one metric might not be always appropriate. It depends on the business objective. You need to retrain the model periodically because there might be data drift, because let's say people would buy different kind of clothes in summer, versus winter, right? So a model which is trained for summer clothes won't work for the winter clothes. You need to retrain it depending on the time of the year, right? And we should also ensure the training data distribution is in sync with the test data distribution. If the distribution of the two are different, the model will obviously fail, right? So these are some of the modeling tips I'd like to leave you with. And that's it from my side. And I'll leave it open for the questions.